that term for it. That's really good. It's even worse because I don't have one of those clicker things, so I'm just gonna be like doing that every couple seconds. All right, so welcome to CS390 neural image processing. This class, well, let's start with the logistics and everything. Of course, Gustavo, you all know him. Office hours, same for 252. But yeah, me, I don't have an office, and first time lecturing for an actual thing, so go easy on me. Just as far as meeting times and everything, going to be meeting once a week, just for an hour. Attendance is going to be part of the participation grade. We'll have 2 free absences, so it's not a huge deal, but you know, it's try to get here. We're going to be doing 4 different projects. One of which is going to be kind of an open thing. We're not going to be, it's not going to be restricted as far as topics go too much. The other 3 are going to be, 2 of them are classification and 2 of them are style transfer, but we'll get into that a little more in the future. Yeah, and we're doing all the coursework in Python. If you don't know Python, it's really easy to learn. You can pick it up pretty quickly, and I don't think we're going to be doing things with it that are too complicated or too language specific. But definitely try to get a little proficiency with it before the first project comes out. And if you do know it, it's going to be very average Python. Also a bunch of libraries and TensorFlow, Keras, SciPy, that kind of thing. So as far as our grade breakdown here, this is it. Don't worry about it too much. I'm going real easy. The homework is going to be assigned really early. It's just there's one single homework. It's not that strenuous, but it's important that it gets done just because it introduces some very important concepts. And I think that's going to be next week. We're releasing that. Labs 18, 18, 20, and 24. Final, by the way, is going to be a group project. Also, no midterms, no final exams, nothing like that. Oh, and as far as the participation grade, we're also going to be having, for a lot of these, a quiz at the start. It's just going to be on the videos that we have assigned, and it's just a little, hey, did you watch the video kind of thing. So this, and we're not having one today, obviously. So what is this course? This is a course on not neural networks in general, not computer vision in general, but just the very small area that is that's still very large, but the area that is the intersection of those two. We're using neural networks to do image processing tasks. Now, that is, we're going to be focusing mostly on the application side of things. We aren't going to be getting too deep into the theory, but we will try to be understanding everything we're doing and knowing what's going on under the hood. So I'd say about 35% theory, approximately. And one of the main reasons that I wanted to teach this course, we're going to be building some real cool stuff. Some real cool sci-fi shit that, oh, probably can't swear here. It's fine.
Take it out in the photo.
Yeah. We'll beep it. Yeah, we're building some real cool sci-fi stuff, and it's going to be great. So I think the next one. Yes, good. All right, so what's image processing? We have a lot of tasks, and they're all ones, or neural image processing. We have a lot of tasks here, and they're all things that are difficult for a computer to do just algorithmically. It needs to have some sort of probabilistic component to it. It needs to have machine learning. So here are a few of them, not all of them by any means. Classification, caption generation, image generation, style transfer is a fun one, data extraction school. In lecture we're covering a lot of them, not doing segmentation because we don't have time for that. Projects, we're very much limiting our scope, though for the last project, of course, you can pick a lot of these. In fact, I encourage you to pick something from one of these three because it'll be a little more interesting. All right, so some examples of neural image processing. We have this handsome devil here with his guitar, and we have this neural network, assumedly. I don't know how exactly they did this, but I don't think they could do it without a neural network. Doing a classification task on it, it probably has hundreds and hundreds of classes that it can assign, and it's deciding that with some likelihood, it's either, it could be a string instrument, a musical instrument, a guitar, an acoustic guitar, and that's pretty good that it's able to pick that out, especially considering how rich this image is. It has me, it's got a pirate flag, it's got all sorts of stuff in there, and it's able to kind of decide that this is the foreground object that it's classifying. This one's caption generation, though I suspect it's kind of pseudo caption generation. So what it's doing here is it's taking the image and it's trying to write some English text to describe what's going on in the image. But it's also, the way this particular CaptionBot.ai is doing it, it's following this specific format every time, which leads me to think it's not like a raw neural network outputting text or even outputting words. I think it's more like tries to identify the situation and then apply some format to it or something like that, which is still very interesting and still pretty powerful considering it's able to figure out not only, it surprised me that it was able to actually figure out which historical figures we were talking about here, but even when it couldn't, it was just normal people, it was able to figure out facial analysis and the such. Style transfer. This is one of my favorite ones. So, let's say you have an image. You like that image, but you really just like the content of it. The style of it's pretty normal. You have another image where you like the style of it. Maybe it's a piece of art, abstract art or whatever, and you want to take that art style and apply it to the image. But if you're like me, you can't draw or paint or any of that. So you make the neural network do it. In this case, I have a picture of a pirate flag. This deepart.io was able to then transfer the style from another work of art to make it look like that, or even another one to make it look like that. It's kind of a circuitry thing. And it does this pretty well, but we're going to be able to do it pretty well also. So here's an image that I found online and forgot to credit, oops, of a nice mountain valley. We have our little lake in the middle here, a little green area, blackish mountain over here, some lighter colors over there. Very nice picture, but what if we want this to style transfer with Starry Night, the famous Vincent van Gogh art? Well, this is the one I wrote, and this is what it tried to do. And I think it maybe not as good as the deep art. It put a little too much style and not enough content in, but it didn't do bad. You know, we still have the same kind of structure. We have the mountain in this kind of swirly pattern, and it kind of resembles the same kind of curves and swirls as in the Starry Night version. And it's doing the same thing with these like little orbs of light up here. It's a really interesting try. And then an even weirder one, Lions at the Gate by Dana Irving. And it came up with this, which is about the trippiest dang image I've ever seen. It definitely did the style transfer. Again, a little more style than content, but I like it a lot. It's definitely abstract, but you can kind of tell it's like a mountains and the sky up there and the water down there. It's an interesting attempt. So let's get into some of the history on the neural networks and a little bit on computer vision, but mostly neural networks. 57, Frank Rosenblatt creates the first concrete model of a neuron, just one single neuron. And again, this is hardware. This is some big, giant 50s computer running in an entire room. And you know, it's not that great for anything, and it doesn't even have a good learning algorithm, but it's an interesting start. It's where some of these ideas started to kind of come together. There were some fairly minor improvements as time went on, but eventually we got to the 70s, where Paul Werbos created a backpropagation algorithm for a 3-layer neural net. It couldn't be any more than 3 layers because he hadn't generalized it yet, but it worked pretty well for that. And it could be used for some really like little machine learning tasks. Just to kind of give a flavor of the decade, in the 70s we also had some great music coming out, particularly like this one. 80s rolled around. We didn't have too much as far as neural networks go in the early 80s, but mid to late 80s, there were some things. General backpropagation algorithm, so now we can learn with as many layers as we want to the neural network. And then we were doing stuff with very primitive convolutional neural networks. I know you've heard about them all over the place because they're the biggest thing right now. Again, some pretty great music came out at this time period. And finally, the 2000s, this is where neural networks got big. In fact, before the 2000s, more specifically before 2011, neural networks were kind of a novelty. They weren't considered that good of an algorithm in a lot of ways. They were definitely had some hype then too, but for the reason that is also part of the reason why they have them now and the reason they've always had hype, they have a really cool name, and that kind of it's something that the press can kind of work with. But anyways, 2009, ImageNet, the classification database, is launched by Stanford professor Fei-Fei Li. She's also one of the people who helped with the course that inspired this course, so that's good. 2011, I cannot pronounce his name. Krzyzewski? Alex Krzyzewski. I'm sorry, Alex. He created AlexNet. Now, this is the spark that started the neural network and to some degree machine learning revolution in the past decade or so. This is when Alex made his network that could classify images way better than anything else could before. And again, this was using a convolutional neural network. which, you know, they've been played with before. They've been played with since the 70s, or not the 70s, was it the, yeah, it was the 70s. They were messing with them since the 70s, it's just, it wasn't, let me check again, I'm not exactly sure. No, it was the 80s. I was around, late 80s. But this is when it really took off. And there was still some good music, not as good, but you know, I think the Fray had an album in 2011, right? I don't know, I like the Fray, they're kind of good. Alright, so let's really start this thing. A little bit of bookkeeping for the starting this thing though. We need to have some sort of dynamic pipeline to handle the process. So I made one up. It's called Max's Chill Image Processing Pipeline, MKIP for short. And it is not any sort of industry standard. It's not the best. It's just one that I made up because I couldn't find. I don't think there's any sort of standard one. I know there's a somewhat vague standard machine learning pipeline, or data mining specifically pipeline. And this one is based heavily off of that one. But yeah. So here's a look at it from a code perspective. We're going to be pretty much always getting the raw data. And you know, you can handle this however you want it to. I'm going to give it in skeleton code, I'm going to give it to you in this kind of situation. But if you want to merge things into one function or whatever, that's fine. But the general gist is we're getting the raw data, pre-processing that raw data in whatever ways we want to pre-process it, use that to train some sort of model, run that model on testing data. In this case, the 0 part of this tuple is going to be the training data, and the 1 part is going to be the testing data. In this case, we're only giving it the X of the testing data, but we'll get into what that means later. Run the model, it can make predictions or have some other sort of output, and then we send that to some sort of evaluation function. So a more graphical kind of view. Again, raw data, pre-process, train, create the model, run the model, evaluate. Okay, so our first task here, obviously there are hundreds and hundreds of image tasks we can do. We're going to start with classification. Let's take a drink real quick.
Always important.
Always important. So classification, basically what we're doing is we are taking our image, which is going to represent our data, and we're going to assign it to be in one of n classes. Now, some examples of this are, have you ever heard of the IRIS data set? It's a bunch of flowers, and you have to classify what kind of flower it is based on like the petal width and all that information. The classes would be the types of flowers, and the actual data would be the petal width or the stem height or whatever. You could also do things like loan data. We did that for 373, I think, when I took it. And in that we had the classes as just a binary, this person will pay back their loan on time or they will not. And we had all sorts of data to work with. A lot of it was irrelevant and a lot of it was super important. So very general kind of problem because there are all sorts of different data sets to work this on. But in general, we're going to say that Y is going to be our class label, lowercase y specifically, and uppercase X is going to be our data, usually in the form of some sort of vector. Again, yeah, stocks is another example. Class label, yep. Oh, and data, another way to talk about one entry in the data is going to be an entry or a tuple or a record. They're kind of used in different fields differently. I'll probably call them either an entry or a record personally, but that's just preference. And the concise goal we're talking about here is trying to find the probability of y given x. Now, we could go into things like naive Bayes, like there's a classifier called naive Bayes classifier, and that does that in a very right to the point way using Bayes' theorem, but we're not going to touch that really because it's not a neural network. Also, it's not really good for image processing. Oh, quick little question. Who can tell me what our x is going to be in pretty much every task we're doing?
The images?
Yep.
In the parts of the image?
Yep, as usually we can have that represented as just a actual multi-dimensional array of pixels, or we can have that as even a flattened array of pixels, which is kind of an interesting idea that even when you have it represented like that, the neural network can still do that. It can still classify fairly well with that in like the MNIST numbers data set. And it's just seeing a flattened version of the picture.
Well, so even if you just have a normal one-dimensional array of pixels and you don't say that there's some adjacency list or which pixels are next to each other,
Oh yeah,
it still behaves fairly well.
if you're just using a simple two-layer neural network and you train that a lot on that image, and it's a fairly small image, you know, it's a MNIST data set kind of thing, that'll do just fine. That'll do in the 95% range. In fact, the weird thing is you could swap the pixels around too, as long as you do it consistently for every image in the data set. So you could have these weird fuzzy-looking images of just black and white that a human wouldn't be able to tell what it is, but the neural network would be like, oh yeah, that's a 9, because we said it was a 9 in the training example, so it's still a 9. Which is part of why neural networks are cool, but also part of why they can be a pain, because they're going to train themselves on exactly what you give them. So if you're not giving them the right stuff, it might not be exactly what we expect. Oh, so here's our updated line. We're just changing some of the text here. In this case, TR is going to be training, TE is going to be testing, and then we have our X and our Y. But otherwise, everything is the same, no major structural changes to the pipeline. So, actually, let's go back here real quick. So with all these parts, it can be kind of daunting because each of these is glossing over a major part. Obviously, our focus is here, or not even the running the model as much as here, training and classification and building the model. But just finding raw data is a big deal. Getting that data pre-processed in a great way is a big deal. And we're going to talk about that stuff, but not as in-depth, of course. And evaluation is what we're going to talk about now. We'll start at the end here and work our way this way. And we're going to learn what makes our model good or not. So, start at the very end. How do we know if our model or our function is a good classifier or not? Well, it can be a trickier question than one would guess. The naive answer would be what?
I mean, given it a set of test data, how well does it perform on classifying that test data? Like, that already has labels.
Yeah, but what specific measure would we use for that?
If you were having something like a neural network trying to take drawings of numbers, try to figure out which number it is. If you train it on images that it hasn't seen before, which already has labels such as the numbers, you're pretty much comparing its output with what the expected output was.
Yeah, but how are we comparing it? Are we just,
So you would have like number of outcomes it gives correctly the total number of inputs you're giving to it.
yeah, accuracy.
Okay.
That's a great start, and accuracy does work in some cases. And in this case, we're gonna try using a binary classification problem just because it makes things a little easier. That meaning, of course, we have two classes, usually falling into some category or not. But we have our binary classification problem, and we have some data we're given, name, age, loan amount, etc. And we need to say if the person's going to pay back the loan or not. Yeah, I stole this directly from the 373. All right. So naive approach, of course, is accuracy, which is, as you said, number of correct predictions over number of predictions total. And again, I'm not saying accuracy is bad. In certain situations, accuracy is a really good evaluation tactic. But let's look at it a little more closely. Specifically, let's break it up into this. Accuracy can also be described as number of true positives. True positives being how many things we said were one and were indeed one, plus number of true negatives, how many things we said were zero and were in fact zero, over our everything. True positives, true negatives, false positives, false negatives. So we have this example here. We have our record number and we have our true classes, and we're going to have our prediction algorithm, whatever it may be, go through. But what if I just decided that as the prediction algorithm, as some really powerful neural net, or not very powerful at all actually, but it decides it's just going to answer Y, yes, for everything. Well, it's going to get a 70% accuracy. That's not a good thing. It's not predicting anything. It's just guessing. And it's able to do that just because it happens to be that in our data set here, there are more yeses than nos. Most people in this data set are responsible financially paying back their loans. It's a pretty good score when it shouldn't be, is what we're saying. We want a more representative score. Especially in cases like this where the main problem here is our data set is not normalized for classes. Obviously, we could do something like try to search out more examples of another class, but then you're into sampling issues, and you don't want to try to fix this problem at the data set level if you can. So, other metrics to try. Precision, proportional of the correct yes predictions. We have our true positives over our true positives and false positives. So it's just checking, this is just accuracy amongst our true predictions. Did we do a good job at predicting whether something is true? Or on the other hand, and of course you can do reverse precision too. That's absolutely a fine thing to do. Have it be true negatives over true negatives plus false negatives. And then we have recall. That is the proportion of the real yes answers that were predicted. Now I think usually these things are used together, but more often they're used in a more integrated way. And that is called F1 score. F1 score is the harmonic mean of the precision and the recall. For binary classification tasks, this is used a lot to my knowledge. It's a pretty good evaluation system, and it's fairly representative of how well the classifier's doing. But again, we don't have to just pick one. We can do all of them if we want, as long as we might have to make some decisions later on how we interpret all of them. But, you know, the difference between, in that final evaluation phase, between deciding, all right, do we want to print out accuracy, or do we want to print out accuracy and also print out F1 score? We just print both. So, yeah, we can use them both. F1 is usually a good start if you want to mess with something. Accuracy is fine too if you're pretty sure your database has, or data set has the same, approximately same number of classes each. But yeah. Here's a little look at that there. So we have our true positives, true negatives, false positives, false negatives, all colored as such, just to make it a little easier to figure out how many we have of each. And that gives us an accuracy of 71%, recall of 0.8, precision of 0.8, and because of that, then we have F1 score of also 0.8. So, what about a multi-class situation? Now we don't have just one class we can choose. We're not deciding whether we're in a class or not. We're deciding which out of 10 or 20 or however many classes there are. So we can't just do a simple precision and recall sort of situation. We could still use accuracy, but again, we have to temper our expectations for accuracy a little bit. So, uniform, what's it say? Yeah. So, basically what you're going to do in this kind of situation is find the F1 score by finding the precision and recall for each of the different classes. Basically treat it almost like it is lots and lots of different binary classifications. There are other ways to do it, but this is the only one we're going to be talking about here. Again, this is not a super in-depth machine learning class as much as it is just a good way of doing it. And a really efficient way to do this in practice is something called a confusion matrix. We have one shown here. This is predicting these different classes, whether some image is a picture of asphalt, concrete, grass, tree, building. It has the total involved as well. And as you can see, this one is pretty good. I believe it's using F1 score here, and oh no, I think it might just be precision. Yeah, but you can do this for any of them. You just would have the anything along this line here is going to be our correct predictions, of course. And again, this classifier is pretty good. It seems to think that asphalt is a building more often than it should, but otherwise it's not bad. And I believe, yeah, that's about it. So we have our links there. You can look over those for a little more information on evaluation, neural networks history, and of course, this, which is going to be the majority of our outside video work. And we're about done with that. Next time we actually start the real meat of the course, which is going to be the neural networks backpropagation and that sort of thing. If you don't have a GitHub, make sure to get one, because that's how we're doing Turnitin. And I think that's it. No homework today. I was just watch the next video. It's up on the website. It'll say like video to watch before next class. And yeah, see you next week.
When's